Hello. In this short video, I'm going to talk about a technique that I use when I want to convert a probability of death to an expected lifetime. Okay, probability of death sounds a little dramatic, and it is. And sometimes you literally are predicting when someone's going to die, like in the biological sciences when you're doing like a study on cancer drugs and things like that. But for most of us, the death that we experience in our work life is a lot more mundane. It takes the form of things like when somebody's going to cancel their service for a wireless provider, or cancel their cable TV, churn, or when a piece of equipment's going to fail, or when an employee is going to take this job and shove it and walk out the door. A lot of times, as data scientists, we have to build models that predict these events. And typically the models, I mean, there's a lot of different models you can build, a lot of different ways you can approach those kinds of problems, but typically what you get out of those models is a probability of the event. For example, a probability that a machine's going to fail, or the probability that a customer is going to cancel. What I'm going to talk about in this video and in this subsequent Jupyter notebook is how to convert those probabilities into an expected lifetime. So, for example, take the probability to cancel and turn that into how long that customer will be a subscriber, an estimate of their length of service or their tenure. Likewise, the probability that a machine's going to fail, and convert that into probability that a machine's going to fail and convert that into the expected life of that machine. Probability that an employee is going to quit and how long they would stay employed. This technique there's a lot of different ways you can do this. This technique is something that I've kind of used more times than I can count over the years, and it works for me. I'm not saying it's the best way to do this or to accomplish this task, but it's just my favorite way. And like I said, it's worked for me. All right, now let's hop over to Watson Studio, which is the Jupyter environment inside of the IBM cloud. And I'm going to walk you through a notebook where I convert a probability to fail into a time to failure metric. And this is for equipment failure, but like I said, this technique can be used for converting a probability to cancel or churn to how long your customer is going to be a customer. Or it could be probability for an employee to quit, how long they're going to be actually an employee, converting that into a tenure as an employee. Anytime you have some death event or some cancellation event, you want to convert that into like an expected lifetime or lifespan. So the data is pretty straightforward. Again, this is equipment failure data. We have an ID, a date, a failure date. So that's the date that this particular machine failed. The difference between the failure date and today's date is how long it will be until the equipment fails, and I'll calculate that in the next step. And this is a probability to fail, and this is just comes out of a gradient boosted tree model, which I developed in another notebook. Here I added the time to failure. So for example, this first line right here for this particular machine, on 12/2/2014, we know that it actually does fail on 4/24/2015. That's 143 days later, and the probability to fail on this particular day is about 35%. And what we're going to do in this technique, I mean, it's not rocket science. We're going to build a regression model that takes this value, the probability to fail, and converts it to a predicted time to failure. All right, so as you deploy this model and you don't know when a machine's going to fail, you can calculate the probability to fail with your gradient boosted tree model or your logistic regression, whatever you're using, and take a separate model, an OLS regression, and convert that probability to fail into an expected lifetime or time until failure. The first step, I think in a lot of different, regression modeling techniques is just to look at the data visually. In this case, I have a time to failure on this y-axis and probability to fail here on the x. And typically, what I'm looking for in this kind of curve fitting and modeling exercise is I'm going to be looking for inflection points. So the line is somewhat linear, but you can definitely see some inflection points. It looks like there's one like around here. And then it looks like there's another one maybe around here. And you don't have to be exact. Guesstimates are fine. Looks like there's another one maybe around here, and then probably one down around here. So I'm going to take those inflection points, and I'm going to use that to build dummy variables, and I'm going to use those dummy variables to regress, to use as regressors in my OLS regression model. Also, I'll take natural logs of the variables, and I'll actually end up the model I build. And this is just general model building type techniques, but I'll actually use in my model, I'll actually use the natural log of time to failure and the natural log of the probability to fail. Here's where I'm building my dummy variables based on those inflection points. Create a training and testing group, always a good practice. And then I build my regression model, ordinary least squares regression model on my testing group. And you can see I ended up with, including only the variables that are statistically significant and theoretically relevant, I get an R squared of 0.224. And looking at that, this is the predicted values, what came out of the model with the actual. And you can see that, there's definitely different distinctive lines, based on those inflection points. And what you're really trying to go for is obviously there's a lot of variation here. I mean, when the probability to fail, the time to failure can be anywhere from 0 to, when the probability to fail is 0.3, the time to failure can be anywhere from basically 0 all the way up to 700 days. But on average, it's around 208 days. So as you apply this, you'll have one model that creates the probability, then a second model that gives the average time to failure based on that probability. We can, it's also good practice to apply the model to the testing data, which I do right here, and it looks very similar, but visually you might not be able to pick up on all the idiosyncrasies, so you want to be a little bit more thorough than that. So I calculated an R squared. The R squared again for the test or the training data is 0.224, calculated on the testing data, and it's 0.208, so very similar. And then the last step is just take that model and apply it back to the original data. So now we have the ID, the date, the failure date, the probability to fail, the time to failure, and also a prediction of the time to failure. Not rocket science, pretty straightforward, but like I said, I'm not saying this is the best technique in the world, but it served me well. I've used it dozens and dozens of times over the last 25 years or whatever. Thanks a lot. I hope that's helpful.